This is Phil Koopman with a tutorial on data integrity. Memory and data integrity involves detecting data corruption using techniques such as mirroring, parity, SecMed codes, checksums, and CRCs. Whenever you're doing data integrity checks, you end up with an arrangement like this. There's a data word, that's the data that you'd like to protect, and you perform an error code calculation of some sort on it. We'll get to those in a minute. And that results in an error code. The error code is a thing that gives you extra information so you can check it against the data word to see if the data word has been corrupted or matches the original data word. A terminology note, there's a thing called a code word, and a code word is simply the data word and the error code taken as a set of data. After you've computed an error code, you do something with the data, such as store it in memory or transmit it. While that data is in transit or in storage, things might happen to it. So later on, you recover the data word and the error code, and you try and figure out, is that data corrupted or not? It's possible that there's been some data corruption, and a typical fault model for this is bit flips. The idea is one or more of the bits in the data word or error code, so somewhere in the code word, there's been a bit flip that changes the value of the data from what you stored or what you sent into what you recovered. The whole point of data integrity is to make sure that the suspect data that may or may not have an error in it actually matches the original data. You do this by taking the data word, performing another error calculation, typically the same error calculation you performed in the beginning, and you match that against the error code. And you say, well, if the computation of the error code based on the received data word matches the error code that was also received, then most likely no memory corruption has occurred. The baseline for memory integrity efficiency is a random hash. Consider if you had a magic function that took the data word and scrambled all the bits optimally, so that the error code was indistinguishable from a random value, completely unpredictable, then in that case what you'd get is that if you have a k-bit error code, there's a 1 in 2 to the k chance that you got unlucky and whatever corruption happened to the code word happens to result in a situation where the error code matches the data word. Think of it this way. If you took completely random data for the data word and completely random data for the error code and matched them, if the error code is k bits, by random chance, there's a 1 in 2 to the k chance they'll just happen to match. So the baseline performance for an error code is that completely random probability of 1 in 2 to the k. Perhaps surprisingly, you can do a little better than that for small numbers of errors, and that's where error code design comes in, and that's mostly what we'll be talking about. I should note that malicious faults require cryptographically strong integrity checks. For this tutorial, we'll assume a non-malicious adversary, in other words, just plain random noise, not a person or computer program trying to intentionally fool the error code. All the error codes we discussed are in fact quite easily fooled by a malicious adversary, so this is only for accidental faults, not malicious faults. The anti-patterns for data integrity are, if you have no checks on memory data, no checks on your program image, no checks on your configuration data, and your values in RAM and other data have no integrity checks, then you're subject to data integrity problems. In life-critical applications, that's a big deal because, as we'll see, memory values will be corrupted over time, and you have to account for that possibility. The other anti-pattern is not having end-to-end message checks. If you're sending messages on a network, especially a multi-hop network, the application layer needs to wrap its own integrity protection around the values it's sending because the data networks might not provide enough protection against corruption of values. Another anti-pattern is using checksums instead of CRCs. CRCs are much more effective than checksums in general and are not that much more expensive to compute. Before we get into how to build error codes, let's talk about the sources of data faults. If data never got corrupted, we wouldn't need error codes. But unfortunately, data does get corrupted on a regular basis from a variety of sources. One source is hardware faults. Network messages suffer bit flips due to noise in the communication line. There's always a bit error rate. It's never zero. So there will always be a case in which some messages are received with incorrect bit values that you need to detect and deal with. Occasionally, you'll get a bad non-volatile memory write, where the bits get written to the memory and degrade over time due to issues with storage, and when they're read, it's not the same value you wrote. In general, there's the idea of bit rot, that storage degrades over time from a number of sources. So anytime you write values out to some storage device, there's a probability that's never zero that when you read it back, you're not going to get the same thing that you wrote out. During computations, you can get single event upsets, otherwise known as soft errors. For decades, it's been known that these happen on a regular basis, but they happen moderately infrequently. So it's not the sort of thing that a programmer runs into very often. But if you have a big fleet of deployed systems and they're safety critical where all the computations have to be accurate, you'll find out that soft errors start to become a problem. Here's a simplified look at soft errors. Soft errors come from cosmic rays entering the atmosphere. Yes, you heard me right. Cosmic rays entering the atmosphere lead to computer errors. It happens the following way. The cosmic rays collide with air molecules. That produces high-energy particles. So high-energy neutrons are ejected from this collision where an air molecule is split apart. Those high-energy particles collide with computer chips. The collision inside generates charged particles moving through the silicon. But charged particles moving through silicon are electricity. And so you get an electric current surge that can change a 0 to a 1 or a 1 to 0 inside a flip-flop in memory. So cosmic rays colliding with air molecules, eventually with low but non-zero probability, will hit a computer chip and flip a 0 to a 1 or a 1 to a 0. They will also change the value of computations in flight in logic gates. So soft errors can not only corrupt values stored in memory, but also cause something like an adder to once in a while produce the wrong addition result. These affect both memory and CPU logic. Any gate in the computer chip can be affected by this and produce a wrong answer once in a while. Error codes typically concentrate on protecting memory values. There are a couple reasons for this. One is that memory circuitry is much more dense than logic circuitry, so it presents a bigger target, but also because error codes are just easier to do with memory. So it is typical to see CPUs without error detection, but memory with error detection. You can also get errors in values from software corruption. A bad pointer, a buffer overflow, some sort of memory management issue can also corrupt memory values. What you'd like is some straightforward way to detect any of these sources of faults in memory values to make sure that you preserve your data integrity. Here's an overview of data integrity mechanisms typically used in embedded systems. A key term is Hamming distance, HD. Hamming distance is the smallest number of bit flips possibly undetected. This is a little bit tricky because you're usually interested in how many bit flips can you detect, and the Hamming distance is the number that are possibly undetected. So for example, if you want to detect all 1, 2, and 3-bit errors, the Hamming distance is not 3, the Hamming distance is 4, because the Hamming distance of 4 means there's at least one 4-bit error in the code word that is somehow undetectable. In general, the higher the Hamming distance, the better. The table on the right lists the types of codes that can give you various Hamming distances. Hamming distance of 1 you get for free, because Hamming distance of 1 means you're vulnerable to any number of bit flips. So that's the baseline, and the point of using an error code is to do better than HD1. Parity detects all single-bit errors. That gives you HD equal 2 because every 1-bit error can in fact be detected. Parity is computed by XORing all the bits in a data value together to produce the error code. You can do this either resulting in a single XOR bit, or you can XOR the bits in a bit position. So if you have a bunch of 8-bit bytes, you can XOR the 8-bit bytes together and get an 8-bit byte result where every bit is the XOR of all the bits in that bit position. That still ends up being a parity computation. It still gives you HD equals to 2. You can also do mirroring to get HD2, but this is a completely different way of handling it. Mirroring is simply you store the value twice. And you say, well, if one of them has a bit flip, the other won't. We won't know which one is right, which one is wrong, but we'll know they differ, so we'll know something bad happened. Typically, you're a little bit more sophisticated than that. Instead of storing the value twice, you store it once, and then you store it a second time with some computation performed, such as inverting all the bits. The reason for that is not about single event upsets, but rather if there's a software defect that wipes memory clean with a single value, for example, there's a loop that puts zeros where there shouldn't be any, and you store a 0 and all ones pair as the mirrored image, then it's less likely that the software will create a 0 in one byte and all ones in the next byte if it's just initializing memory. That does not increase the Hamming distance, but it's a good idea and certainly better than just storing the data twice and being vulnerable to a memory initialization loop. We'll get to CRCs momentarily, but there are some situations in which a CRC is only able to provide HD equals 2 as well. If you want HD to be 3, then you typically use a Hamming code, which is single error correction codes to correct single bit errors, some CRCs, or short Fletcher checksum, and we'll get to Fletcher checksum in a moment. The idea at HD equals 3 is you have the ability to detect 1-bit errors and 2-bit errors, but you can spend the Hamming distance either to correct a single error or to detect both 1 and 2-bit errors. You cannot do both at the same time. To get Hamming distance 4, you need to use a CRC or a single error correction double error detection SecDed code. If you're using a CRC, typically you're using a Hamming distance of 4 to detect all 1, 2, and 3-bit errors in the code word and not detect all possible 4-bit errors. SecDed codes are a little more special. SecDed codes are codes specifically constructed to give you Hamming distance 4, but spending that HD equals 4 to be able to correct all possible 1-bit errors and also be able to guarantee detecting all 2-bit errors. Typically, a SecDed code is just a single error correction code with an extra parity bit that gives you that extra bit of Hamming distance. The size of a SecDed code is about log 2 of the number of bits plus 1. So they get expensive for really long data words, but for things like 32-bit words or 64-bit words that you would use in a memory store, they're actually quite practical and widely used in high-integrity computing. If you want a Hamming distance of 5 or more, you end up using a CRC, which we'll get to next. Checksums are a specific error coding technique that is relatively cheap to compute and provides reasonable coverage for some situations, but is limited to low Hamming distances. We'll go through the usual suspects for checksum computations and explain the differences and their capabilities. As a baseline, consider this chart of probability of undetected errors with code word length. The 1/2 to the k line is a theoretical anchor point against which we can compare other error detection codes. That anchor point is chosen because if you have a completely random code word and a k-bit error code, there's a 1 in 2 to the k chance that by random chance, the error code will correspond to the data word and you'll get an undetected error. In other words, somebody's replaced all your data with completely random garbage, but with probability 1 in 2 to the k, you won't know it and you'll think it's good data even though it's bad data. The question is, can we do better at a moderate computation cost? Let's start with the simple checksums, which are additions across all the data word bits. The simplest computation is to XOR all the data words together. This chart is for 16-bit data words, so the idea is you break your data into 16-bit chunks, you XOR the 16-bit chunks together, and at the end you get a 16-bit error code, which is a bitwise position XOR of all the bits in that position and all the other words of the data word. That gives you much worse than random hash performance, but it does give you Hamming distance 2. This may be a little counterintuitive. On average, your probability of undetected error is worse with an XOR than a random hash. However, it will guarantee that no single bit error is undetected, which is something a random hash cannot actually do. If your needs are extremely modest and you have essentially no computation power because you're building a hardware circuit, XOR might be okay, but it is a very weak capability. If you have a little more computation power, and especially if you're running in software where addition and XOR cost the same typically, you can use a 2's complement addition. And that gives you HD2 but with a little bit better, where lower is better, undetected error probability. The reason for this is your performance will increase the more you mix the bits together of the data word to make it harder for a single bit flip to go unnoticed. 2's complement addition checksum detects all 1-bit errors and most, but not all, 2-bit errors. You can use a 1's complement addition, which wraps the carry bit around, and it does a little bit better, but on this graph you can barely tell the difference. If you're going to use plain addition for a checksum, you should use a 1's complement addition checksum if you can. It is the best of this family, but as you can see from this chart, you can do much, much better. There are a couple complex checksums, a Fletcher checksum and an Adler checksum, that are more complicated but still rely on addition as their primary function. A Fletcher checksum keeps not 1 running addition across the data word, but 2 running additions. For a 16-bit Fletcher checksum, it would keep 1 8-bit counter, which simply adds all the bytes as it sees them. It would take a second 8-bit counter that adds up the values in the first 8-bit counter. It turns out that the interaction between these two additions gives you better performance at short word lengths, and in fact will get you Hamming distance of 3 up to a certain breakpoint just under 2K bits for a 16-bit value. Longer Fletcher checksums, for example a 32-bit Fletcher checksum, has a similar property that it gives you Hamming distance 3 at small values and then changes to Hamming distance 2. But even at Hamming distance 2, it does dramatically better than a simple addition because you get a more complex mixing, and therefore it's much more difficult to find a 2-bit error that just happens to get past all those complicated addition functions to result in an undetected error. An Adler checksum is the same idea as a Fletcher checksum, except when the counters roll over in a Fletcher checksum at the values of 255 in a 16-bit Fletcher checksum, the Adler checksum wraps the counters around at a relatively prime modulus, which gives you somewhat better mixing, but at the cost of having a couple values that are never really used. While this seems appealing, the loss of the extra values impairs the error detection ability, and it ends up being that the Adler checksum does not actually give you substantially better performance, and in some cases it's a little bit worse. And especially considering the additional complexity of the calculation, it's almost never worth using an Adler checksum. If you want to use this type of checksum, you should be using a Fletcher checksum. CRCs do even better than checksums. As you can see from this curve, CRCs are dramatically lower than the Fletcher-Adler checksum. This is because CRCs are based on a convolution-style algorithm, which does very thorough bit mixing. Other checksums, including Fletcher and Adler, are based on an addition operation which only mixes adjacent bits, and therefore is not as thorough at mixing bits. Even better, you can see for small data word lengths, CRCs provide higher Hamming distances than 3. The CRC, Cyclic Redundancy Check, sometimes called a cyclic redundancy code, is a far more powerful error detection mechanism than a simple checksum. The mechanism works the following way. Thinking about a hardware implementation, there's a shift register. Bits from the message are shifted into the register 1 bit at a time, with a low bit of the shift register XORed with a message bit, and then fed back into various stages of the shift register. All the boxes, each box is a bit, is set to an initial value, and then for every incoming message bit, the entire set of boxes is shifted 1 bit to the right. The bit popping out the bottom is XORed with a message bit that's coming in and gets fed back to mix with the other bits, including being put into the top box of the shift register. If you have a 64-bit message, then this shift register is shifted 64 times, once for each bit of the incoming message. The accumulated result in the shift register is the error code value, sometimes called a frame check sequence FCS for network messages. From this picture, you can see the red arrows are where the message shift register value is combined with the bottom bit and then XORed back in to various stages of the shift register. That performs mixing to scramble the bits as you go. An interesting thing about CRCs is even though this hardware mechanism clearly does some mixing with the feedback and the XORs, there's some actual math behind what's really going on here. The math is based on polynomial division. The way to conceptualize this is that the shift register has binary values in it, those are the data bits inside the boxes, but also has a feedback polynomial, where a 1 in the binary polynomial value corresponds to a place where the feedback is inserted into the shift register, and a 0 corresponds to a place in the shift register where there is no feedback and the bit is simply transferred from a box on the left to the box on the right. In this picture, the red arrows into the feedback correspond to 1s in the polynomial shown at the top. There are many different polynomial choices, and this is simply one value. There are other possible values. In this case, if you look at the binary number represented by the feedbacks, 1011, 0100, 0001, hexadecimal B41, that corresponds to a polynomial of x to the 12th plus x to the 10 plus x to the 9 plus x to the 7 plus x plus 1. The 1 is actually an implicit value that is not shown in that hex value, and the plus 1 is the feedback of the message shift register at the end. This is a polynomial that you can factor, as you may have had in math class, and you can notice that if you break it up into its factors, there's a factor of x plus 1, where x plus 1 implicitly means that there's a parity computation. So if you have a polynomial used for a CRC and it has a factor of x plus 1, in other words, it's evenly divisible by x plus 1, you know that the result will detect all odd number of bit errors, just as if there had been an explicit parity bit. Where the math comes in is what you're really doing is you're representing the message also as a polynomial. So if it's a 64-bit message, it's either 01 times 2 to the 64, plus 01 times 2 to the 63, and so on. If you represent both the feedback as a polynomial and the message as a polynomial, then you can think of a CRC calculation as doing a polynomial division of the message divided by the feedback, and the value that's in the CRC shift register at the end is the remainder of the division. The CRC calculation is doing a polynomial division over Galois field 2, which for our purposes means that it follows Boolean algebra rules instead of integer arithmetic laws, and the resulting remainder is the error code. The feedback polynomial selection matters. Some polynomials are good for error detection, and some are really bad. Some of the bad ones include commonly used international standards, so you cannot simply say, well, this polynomial is popular, so it's good. That's not always true. There are also some rules of thumb that may be true but are misguided. For example, there's a common rule that you always want x plus 1 divisibility to get high Hamming distances, and that's simply not true. X plus 1 always gives you parity, but sometimes getting parity actually makes it a lot harder to get a good Hamming distance. Despite many years of mathematical approaches trying to derive good polynomials, for Hamming distances higher than 4, the most effective way to find a good polynomial is brute force search of trying all the polynomials to see which one does best. The bad news is that the only way to know you found the best possible, or at least a good polynomial, is to try all possible polynomial values. So for a 32-bit polynomial, that's 2 to the 32 possible feedback patterns. The good news is this has already been done for you, so you can just go look up the answers. These tables show the result of evaluating every possible polynomial over every possible data word length. The square in this table is for a column, which is the CRC size in bits, and a row, which is the Hamming distance. Each cell has a value where the top unbolded value is the maximum data word length at which that Hamming distance applies for that size CRC, and the bottom row within a cell is the CRC value that gives you that performance. These tables have exhaustively explored, with only a couple exceptions, all the possible polynomials between 3 bits up through and including 32 bits, and even some polynomials beyond that, and will tell you the best or at least good polynomials to use for each Hamming distance possible at each data word length. As an example of using this table, consider that you want Hamming distance of 4 and you have a 256-bit data word. The question you're asking is, what's the smallest, fewest number of bits CRC I can use that will give me Hamming distance of 4 for 256 bits of data word? If you look at the Hamming distance for table row, you go out and you see, well, there's one at 246 bits, but that's smaller than 256. But there's another one at 501 bits. 501 is larger than 256, so a 10-bit CRC will get you the Hamming distance you're looking for, because it will give you Hamming distance 4 or better for everything below and including 501 bits. The polynomial in this case is hexadecimal 247. As another example, if you want Hamming distance 6 for 128-bit data word, you look at the HD6 row and you'll find out that 114 at 15 bits isn't quite enough, but a 16-bit CRC will give you Hamming distance 6 up to 135 bits. You only need 128, so that's the one you want, and the polynomial is 9EB2. As you can see from the 32-bit column, you can get impressively long data words with good Hamming distances if you pick the right 32-bit CRC. The best practices for data integrity include the following. Ensure you actually have sufficient data integrity. Every safety-critical embedded system will suffer bit flips in its memory, in its logic gates during its operational lifetime. Not often, but they will happen. To mitigate against these, you want to be using CRCs on network packets. You should add a CRC on your flash and non-volatile memory data and periodically check it to make sure the bits are still the ones that are supposed to be there. And you should use an appropriate memory integrity check on RAM depending on the criticality of your system and the degree to which you have multiple redundant RAMs with the same value at the architectural level rather than just being managed by software. The pitfalls for data integrity are many and varied. It is common for life-critical system designers to assume that mirroring data values is enough, but most often it's not. If you're doing mirroring, ask yourself, did you mirror data on the stack or just longer-term memory? Did you mirror data on values inside the operating system? And so on. Mirroring may not be enough because it's very difficult for an application programmer to actually mirror a lot of the internal state of the system that determines its proper operation. Another pitfall is assuming that doing data integrity measures for just things stored in memory is all you need, because in fact, data corruption can occur during calculations if the cosmic rays cause a bit flip inside an adder or a program counter or things like this, which aren't really in memory, but they are very susceptible to those types of disruptions just as memory is. Another pitfall is using a checksum instead of a CRC. While CRCs are a little more complicated to understand and the calculations a little more involved, they just aren't that slow, especially if you use one of the well-known table lookup approaches. For most applications, it is worth doing the CRC calculation to get the added error detection benefits with no change in storage size. There are many subtle pitfalls for the unwary. If you're going to be using error codes in safety-critical embedded systems, this tutorial is merely an orientation session, and you need to dig deeper, for example, by looking at an FAA report on the evaluation of communication networks in critical systems, which has many more details.